Hear me?
Talk about homework. So today will be the last homework assignment available on campus.
Professor, can you hear me? Professor?
Okay, and we can make it do. I think I might make it due Tuesday the 11th. Let's see. Fine. No, we can't have assignments due during that time. So let's do a week from today on the 6th.
Professor, I have a question.
Okay. And I also want to put a reminder that if you missed any past assignments, you can write to me and I can give you an extension so that you can work on those things until the end of the semester.
Professor, I have a question.
Even in exams, it's okay. I can, well, let me see. If you haven't taken the exam, then I can unlock it. But if you've already gotten a grade, it's just going to stay at that grade. Everyone did a good job on their test. Okay, and now we're going to work on notes. So I
Professor?
want to go back over walk, path, circuit. And today I want to talk about Euler path and Euler circuit. Next week we might introduce isomorphic graphs if we have time. And I'll make them kind of easy. If it's isomorphic questions, it'll be kind of easy, and that way it can be on the homework. Okay.
Professor?
I'm going to figure out what section this is in before we get started. So I used the book a little bit to make the notes, but you don't need the book in this class. However, they are from section 6.2.
Professor?
Paths and circuits. Just a sec. Okay, let me see. All right, it's more like, let's see, Euler's path there. Okay, still chapter 5.2. It introduces a path and a circuit, but we're going to talk about walks and then paths and then circuits. A walk is a sequence of vertices, each connected to the other one by an edge. And then a path is a walk, and you don't reuse edges. Oh, yeah, I think let me check the volume. Let me see. Okay, so is there a question? Should be able to hear.
Can you hear me now?
Yeah.
Okay, perfect. I was totally Juan had messaged me saying he could hear me, so I just want to make sure you could. I had a quick question regarding like the walks, paths, and circuits. Sometime like when we're going over notes, can you go over how like I don't know if you call it like a hierarchy, but like how if one's this one, then the next one's this one and that one, and then if it's circuit, it's also a path and a walk. Like I remember we went over it yesterday or 2 days ago, but like when instances where it would be a circuit or a path or a walk.
Yeah, we're going to definitely do examples.
But like if it doesn't meet like the criteria, yeah. Cool. All right, thank you.
And I think what would be good is if I drew this. Usually first I see is it a walk? And if it is, then can it be a path? And then if it's a path that starts where it ends, that makes it a circuit. And we're going to practice. That last part here is let's see, don't reuse. I think it's to dash. And then this one is the start has to be the same as the end. Okay. Yeah. Looking. Here. Okay. We're going to draw a graph, and then I'm going to try to create some examples. Or you could help me make some examples too. The graph, it starts as a square. A, B, D, F. We're going to put a dot, a vertex right here called C. And then connect C with B. Okay, first let's just do one of each of these. Let's do a walk and a path and a circuit. So a walk, you just need to be able to go from one dot to the other using an edge, and you can redo an edge, like you can go back and forth over edges. You just can't go from here to there, like you can't make that kind of jump. CD. But I could go C, B, D, F, D, just going to call that good. C to B, B to D, D1 over to F, and I want to send F back across that edge, which makes it a walk, which is okay to reuse an edge. Okay, a path can only use each edge one time if you do use it. So let's go A, C, F, D, and that'll be it. So I was able to go from that vertex to the next one using an edge, and then from here to here was okay. From here to here, I had an edge to travel on. So it is a walk and it is a path. But we're going to choose the strongest definition, so we would say path. Okay, a circuit needs to start where it ends, and it has to be a walk, and it has to be a path. But if it's all three of those things, we're going to say that it's a circuit, like the best definition that matches. Okay, we're going from B to A to C to B. So they start at B and end at B. I was able to go from each vertex to the next one using an edge. And that's it. So, and every edge was used one time. So we had the walk part, the path part, and the circuit. Okay, next we want to make a walk that starts at A and ends at D. Start at A, and as long as I go from one vertex to the next with an edge, I can do whatever I want. Like I can go A, C, F, D if I want to.
Professor, can I try to create an example of something that wouldn't be a circuit, but it would be a path?
Yeah. Okay. Oh, but it is a path.
So like if you had one like going in circles and going like A B D F A B D F, but it would be reusing it. So or no, that wouldn't be a circuit. If it all started and ended at A, but like passed through all of them like twice, like A B D F A B D F A, that wouldn't be a circuit because it's. Oh wait, I confused myself. I'm sorry.
Yeah. It would also not be a path if you go through an edge from one more time. So it's not a circuit or a path.
Right. So it'd be a walk.
It would be a walk.
Because it doesn't meet the criteria for the two other strong ones. Yeah.
Yeah. If it's not a path, then it's definitely not a circuit. You'd have to go all the way back to the beginning at walk. Let's see. I have other ones to pick.
Thank you.
We will do this one, and then we're going to do something like. And you're welcome. That's a good question. We're going to do a path that is. Oh, cool. Yeah, I said a path that's not a circuit. That's what you asked. Nice. And a walk that is not a path. I think that's the one we just talked about. So we'll write something like that down first. A walk that is. Okay, let's do this one. It's a walk, so it can reuse edges. And I want to reuse edges, that way it won't be a path. So we're going to travel around. Let's do A, B, C, A, B, C, A. So we can start where we end, like was mentioned before, but it's still not going to be a circuit. A, B, C, A. And we're going to go B, C, A again. Okay, so even though there's an A at the beginning and an A at the end, you might think it's a circuit, but you go along A, B, and then from B to C, and C to A. And then you reuse AB. So now it's not a path. And again, if it's not a path, it's not a circuit. So you have to say it is a walk. Okay. I'm going to just pick one of the edges that we did repeat, edge AB. Okay, this one, we'll find some kind of example up here. So it's not a circuit, so we don't want the start to be the same as the end, but it is a path. We do want to use an edge only one time if we use it. Okay, let's go F, D, B, C, and then don't go back to F because that would make it a circuit. Go somewhere like A. I'm going to take F to D. F to D. So use this edge one time, that edge one time. I'm going to go to C. That edge is used once. But if I go to F, then it's a circuit, which we're saying don't pick a circuit. Let's go up here to A. And I'm just going to end it there. So that's a good enough example. Okay, some more examples. This one it has a kind of triangle, like this vertex goes up to that vertex, goes over here, this connects, and then this goes down. And there's a vertex. They are labeled A, B, C, D. And we want to find a walk that starts at A and ends at D and visits every edge at least once. And ends at vertex D and visits each edge at least once. Okay, and let's see. Let's get this graph looking a little better. Okay, walk means we can reuse edges. So as long as I just go from one dot to the next, that's like all of the requirements we need. We're starting at A, we need to end at D, and we need to visit every edge at least one time. So this part, this part, this part. Starting at A. We can go, we can travel around the triangle A, B, C, A. So go over here and here and here. I need to go over this edge right here. So let's go back to C and then down to D. Okay, so I chose A, B, C, A, C, D. Let's go again with, that will go from here, 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 back, back, there. All right, next time, the next part is find a path that travels along every edge once and only once. A path. Okay, so you have to use every edge one time. But also make sure that you use all of the edges. Okay, let's just clean this here. It's the same graph. I just want to start. Okay, let me think about this. Let's try starting. Let's start in a place that I kind of know won't work. So let's start at C. And let's try to find a path that covers all 1, 2, 3, all 4 edges one time. So I could go from C to B, B to A to C. Oh, actually, that seemed to work out. I was able to go C, B, A, C, down to D. Okay, found one that worked. Let's write it down, and then let's try another vertex and see what happens there. So if I go from C to B to A to C, and down to D. Okay, I guess one that might not work would be something like starting at, let's try starting at A or B, either one of those. So by the way, this is a correct answer. I just want to play with this question a little more. Let's try using B first. If I start at B and go, let's go to C, then to A. And I would go either to B and then reuse that edge to get that CD edge at the end, or I'd have to turn around and reuse this edge, AC, in order to cover everything else. So there's not a good path that uses every edge if you start at vertex B. Same thing if you chose A. Let's try vertex A, send it to C. We could do CD, but then we'd have to use that edge again to get back here and go over CB, BA. So we could go this way, and then this way. But now you reuse this edge if you want to get that last one that we haven't covered. So this one won't work, and this one wasn't working. So we found a good example from vertex C, I think. Let's move on. Okay, skipping that. Okay, so there's two more definitions for today, Euler path and Euler circuit. And it's not spelled how it sounds, it's somebody's last name. Maybe I've talked about this before. Depends on what we covered earlier. Forget all the stuff we talk about. Euler. I think we drew Euler diagrams. Anyway, an Euler path. It spells E-U-L-E-R. Is a path. And it uses every edge once. Okay, so it's a path, which means, I forgot to write that. An Euler path is a path that uses every edge, all of the edges, one time. Okay, and an Euler circuit is a circuit that uses every edge exactly one time. And that's it. So we're going to, I think we'll practice a few of these, but I also have still more examples for just plain old paths and walks and circuits. But there's this new kind of more strict path. An Euler path has to use every edge. And an Euler circuit is a circuit, and that has to use every edge. So I used to have a packet with all of these problems to see which graphs have Euler paths and Euler circuits, which leads to a result. Okay, we'll do a few together. But there's a theorem we're going to hopefully get to at the end today. Yeah. Let's do this one. Looks cool. It goes here, here, vertex, vertex, edge. Over this, and then we're going to put vertices this vertex like this. So to me, it looks like an arrow. And we don't need to label these, but it might help just to talk about an example. Like as an example, let's go A, B, C, D, E, G, H. Okay, so this will help describe like where I'm trying to travel on this graph. Let's see, is there an Euler path? Not just a path. Okay, so we're looking for a path, and we need to cover every single edge one time. All 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them. I think I would want to, I'm going to try starting at C. So let's start here and go C, D, A, B, C. It's okay to reuse a vertex, but we can't reuse any edges. So let's just try this out. All right, we're going to go around the triangle, C, D. Let's go over here, C, D, C goes to E, and let's try going to F, G, H, F, I, J, H. Cool, I did it. Okay. It's going to be a really long sequence. So let's get it down here. Okay, so I was able to find an example. We go C, B, A, D, C. That takes care of all of those edges. And this edge, C, E. And then I went F, G, H. And you can take H back to E, because even though you visit E again, the vertex, we haven't covered that edge yet. So we're using this edge just one time, which is the goal of having a path. And then let's go down here, 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 which covers all of the edges and makes it an Euler path. Okay, we took H to carry it down here. H went to E. Then we sent E to I, which went to J. And that goes back to H. Is an Euler path. Let's go with this graph. Actually, let's save it for later. We're going to try a triangle connected to another triangle. It S, T, X, Y. Can we find an Euler circuit? Or try to find an example of an Euler circuit. Oops, UL. Okay, so a circuit is a path, so we have to use each edge one time. And a circuit ends where it starts. And an Euler circuit uses every single edge one time. I'm already kind of thinking, if I started at W, I might travel along this triangle. If I start at Y and do the triangle, I'd have to cross back over or go around the triangle some more. So let's try starting with X. Let's see if we can take X around the graph and end at X. Start at X, travel around the graph, get back to X. Okay, let's take X to S. And we'll go down to Y. And then back to X. Okay. And let's go this way to T, down to Z, and then back to X. So I did it like that, a circuit. So you start where you end. We use every edge one time, and we covered every edge with that sequence. Like we went around the whole graph. Okay, it's going pretty cool, but we want to try one that doesn't have any. Go like this, dot, straight down, straight down. Let's go over this way. Dot, up, up, and connect, connect. let's do another dot, 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 connect, 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 connect. And I'm trying to think, do I need any? A little more just in case. So we're gonna put 2 dots here. Let's see what happens with this graph. All right. Let's start it with labeling it like A, B, C, D, E, F, G, H, I. Oops, H, I. J. Okay. Let's try to find a Euler path. And then if we can find an Euler path, then I would like to try to find an Euler circuit, but I kind of tried to pick this graph so it wouldn't work out. But we'll play around with covering every edge one time. So this one's use an edge once and only once, and this one says use all of the edges. Let's try starting at A. If we want A, let's go like A, E, H, I. I feel like I can cover this part. Let's go A to E to H to I. Okay, let's go. Just go around the edge. I goes to J, goes to K, goes to D. Let's keep on going this way. Let's take D over to C. And then let's keep going around the edge with C to B. And then let's pause. Okay, thinking. So if I go further and get to the vertex A, and I want to still go over those edges over here in the middle, I'd have to either reuse AE or reuse AB. So it wouldn't be a path anymore if I did that. Let's go here down to F. But again, I kind of have this problem where I need to cover this edge. But if I go FE, I either have to come back to F and use that edge again to get these edges covered. So then we could go, I guess, F to G, and then send that somewhere like to C or to J. But if you go to B, F, G, C, now you have to cross this edge or some other edge to get this missing one and that missing one used. So that one's not going to work. Let's see, like if I go to F and then to G, let's clean this up again. All right, A, E, H, I, J, K, D, C, B, down to F, over G. I kind of hit either J or C and get stuck. Z. And then like forward. We're going to try one more time, but after that, we're going to just state some theorems. So let's just use the same graph. Let's start somewhere else. Let's start like, where do we have a problem? We had a problem trying to cover this part here. Let's start trying to take care of the middle. So let's go F, E, A, E, F. Let's try that. Okay. F to B, B to A to E, back and F. Let's go around the square. Let's do F to I. And then I to H. H to E. But then you have to either cross that edge again, or backtrack and reuse the edge you just went over, or go over that edge up here, and that edge and that edge, and so on. So I'm starting to reuse edges, which makes this not a path. And if it's not a path, if you can't find a path, it's not going to be an Euler path. Okay, so let me pull up the kind of cheat sheet. There's a trick to this. Okay, the first one I need to find. Okay. We've talked, so I found the notes. And we have talked about connected graphs and disconnected graphs. So the theorems are for connected graphs. So remember, that means we have, did we talk about it? We talked about connected and disconnected and components. Let me be sure. Wait, was that it? Oh. Yeah, we did. We said it's connected if there is one piece or component. So this means too many notes. We'll have an Euler path if it has all right, I need to find it. Oh, oops. I found it. Okay. It's here. Okay, it has two odd vertices. Awesome. So that's the first theorem. And by odd, I mean the degree of the vertex is odd. Let's see. We'll go back and practice with more graphs about finding Euler paths and circuits using this theorem. Okay, the other one is a connected graph has an Euler circuit if there are 0 odd vertices. Euler circuit. If it has 0 odd vertices. Okay, I kind of want to pick some of the graphs you've already looked at, and of course I have a lot more graphs to do. But one of them was a triangle connected to another triangle. Okay, so even or odd vertex is talking about the degree. So write the degree of all of the vertices. This is 2, 2, 2, 2. 1, 2, 3, 4. So even, everything's an even vertex. So this one has all evens, which means 0 odds. So there will be an Euler circuit. We're going to put EC for Euler circuit, and we're going to put EP for Euler path. Okay, let's try to draw a graph like the one that wasn't working. It was a square. And we went over, connected over again, and connected. Actually, there was more, wasn't it? It had a piece like this. Okay, we had that graph earlier. And I tried to just travel around and see if we could find an Euler circuit or path. But now I can just check all of the degrees, and if there's 0 odd vertices, then it would have an Euler circuit. If there are exactly 2 odd vertices, then there's an Euler path. Otherwise, there's not a circuit or a path. All right, this one is degree 2. Degree 2. So degree 3, degree 3, degree 3. Okay. This is also like 3, 2, 3. And here's a 1, 2, 3, 4, degree 4. This is degree 2, and 1, 2, 3, degree 3. Okay, so either it's all evens, which makes it a circuit, but that didn't happen. There's an odd vertex, right here. Or it has exactly 2 odds, but this one's odd, this one's odd, this one's odd. So we already have 3 odds. It's not going to work. There's like 1, 2, 3, 4, 5, 6 odd vertices, which is more than 2 odd vertices. So there's no Euler path or circuit. Okay, we still have about 15 minutes, and let's just keep playing with basic graphs, but we might try, and we'll do it next week. There's some cool word problems that we can start to use with Euler paths, the theorem for Euler paths and Euler circuits. But there's no rush. All right, let's try this graph. Say square with a triangle on top. We're looking for Euler paths and Euler circuits. So let's just check out all the degrees. This one's a degree 2. This one's degree 2. Degree 1, 2, 3. Degree 3. Degree 2. Okay, there are 2 odd vertices, which means we have an Euler path. This one. Then we're going to do cool. This next graph. It's a big outer triangle. And then we have this inside kind of triangle like this. Okay. Is there an Euler path or circuit? Euler circuit. We're going to check out the degree of every vertex and use the theorem. So this is degree, well, we'll use one of the theorems if we can. Degree 2. Okay. Degree 1, 2, 3, 4. That's a 2. This is a 2. 1, 2, 3, 4. Cool. 1, 2, 3, 4. 1, 2, 3, 4. Every vertex was even, 2s and 4s. So we have an Euler circuit. And also, if you have an Euler circuit, you also have an Euler path. So we're going to choose the stronger, which is Euler circuit. Alrighty, let's try this one. It goes a dot down to a dot, and then do another dot. Let's do one more. Over vertex, over vertex, over vertex. So that's 1, 2, 3, 4 vertices on the bottom, and then like starting here, 1, 2, 3, 4 vertices on this side. And these two are connected. We're looking for an Euler path or circuit. Okay, let's check out the vertices. This one's degree 1. This is degree 2. Degree 1, 2, 3. Degree 2. This is degree 1, 2, 3. Degree 2. Degree 1. Okay. So we need every vertex to be even to have an Euler circuit, but you don't have all evens. There's like a 1 and a 3 and a 3. So this is not going to happen. Path. To have an Euler path, there needs to be exactly 2 odd vertices. And this one has 1, 2, 3, 4 odd vertices. So there's no Euler path and no Euler circuit. How do you guys feel about these? I have a lot of examples, so I'm just trying to pick ones that I like. And maybe we'll do like 2 or 3 more. But do you have any questions or concerns? Other paths and other circuits. Okay, I'll pick 2 or 3 more that I think are fun. Let's go with this graph. It has a square. And this other square kind of built up on top. And on the side, there's another square coming out here. Okay, is there an Euler path or Euler circuit? I'm just going to put shorthand at the top. Euler path 2 odd. Euler circuit 0 odd. Okay, neither would be more than 2 odd. So let's check out all the degrees. So 2's on the outside. Every corner. Looks cool so far. Let's go here. This is 1, 2, 3, 4. 1, 2, 3, 4. I think we got them all. This. Cool. We have all evens, which makes this an Euler, a graph that has an Euler circuit. It has 0 odds, has all evens. I'm just kind of thinking, if it has an Euler circuit, it also has an Euler path, but you use the stronger choice, the better choice. Circuit path or neither. Last one, let's do. It's a square on top of a square. And we're going to put a edge that kind of bends along the side and this side too. Euler path or circuit. So can we have an Euler path in this graph? Let's check out the degrees or the vertices. So this one's degree 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. This is 3. Okay, all odds. So we want all evens to have a circuit, so it's not a circuit. You can have exactly 2 odds, which makes it a path, but there's more than 2 odds. So this one's neither. All right, so that's about it for today. I just want to kind of preview what we want to cover next week. So we're going to use these theorems to find out if you can use something like a graph that represents a map, and you want to make your trip but only visit every place one time and not revisit any of the places you've already gone to. So problems like that. Let's see. That kind of stuff will be on your homework. Question like, and then again, I'm almost done. So let's see. I have one like a politician wants to canvass a neighborhood and they want to end where they started, which is where they parked their car. Is it possible for the person to visit every street exactly once? And we'll talk about having different locations or different graphs. So we'll get to that when we meet next week. Right, have a good weekend. Thank you. I'll have your homework
And
up.
homework 7 will be posted by end of day today.
Yeah, I'll make homework today.
Perfect. Thank you so much.